It's recording, and it recorded last time. I really hope I thought it was recording last time. All right, so kind of summary of where we are. As far as solving things analytically, when you're dealing with a limit, if you get 0 over 0, that means you have to do more work. And the more work could mean factor, get a common denominator, multiply by the conjugate. There's another one where you just have to multiply a bunch of stuff out. And after you do all of this algebra stuff, something cancels, and then when you plug in, you don't get 0 over 0, and whatever you get is your answer. So, like, we know how to handle it if we plug in, and if we get like 0 over a number, we know what that answer is. That's just going to be 0. If we plug in our limit and we get some number over 0, well, that means you've got a vertical asymptote, and so our limit's going to be does not exist. And whenever you get 0 over 0, you've got to do more work. And I just talked about all the different types of work you can do algebraically. Well, that's fine, except if I give you this thing. If I say, what's the limit as x goes to 0 of sine x over x? Well, sine of 0 is 0. And of course, at 0, you get 0, 0. All right, that means that's an indeterminate form. You don't know what's going on, so you've got to do more work. And actually, let me pause for a second, because a couple of people asked in the second period, and I just want to make sure we can sort of set some ground rules here, some things, some common knowledge. Do you need to know all of the trig function, like what's sine of pi over 3 and tangent of pi over 4? Yes, you need to know those. Those are going to come up fairly often. What's going to come up almost daily are these values. And everybody in here needs to know that when you take sine of 0, you get 0, and when you have cosine of 0, you get 1. That's all back to your unit circle, where you have, here's our unit circle. At 0, we're here. The x value is 1. That's where this comes from, and the y value is 0. So, yeah, the trig stuff where you got to draw the unit circle to figure out if it's square root of 3 over 2 or 1/2 or what have you. Yeah, you need to know that, and that's going to show up. But you really need to make sure that you know sine of 0 is 0 and cosine of 0 is 1. Now, that being said, let's talk about this problem. So, in dealing with sine x over x, you get 0 over 0. You have to do more work, and good luck factoring that. It's not going to happen. Good luck multiplying by a conjugate. It's not going to happen. There's no algebra thing that we can do to manipulate this. So, sort of a little history about this particular problem. The official way that I'm supposed to do this, it takes about 10 minutes. Believe it or not, I have a lot of fun teaching it. For years, that's what I did. And what I found was at the end of that 10 or 15 minutes, 2 or 3 people had an appreciation for it. Everybody else was just bored to tears. And I finally decided, you know what? It's not that big of a deal that I go through the whole process of how I found the answer. What I'm going to do is basically just give you the highlights. And so that's what I'm going to do. I'm going to give you the highlights of what happens to solve this problem. And at the end of the day, we're just going to talk about the result and how we use that result. So, here are the highlights. So the highlights actually involve, it's something called the Squeeze Theorem, or some books call it the Sandwich Theorem. And here's how it looks. If I write down, so if I write down that f of x is in between g of x and h of x. All right. So if I write down like the f of x is in between these two functions, what that means is, if I'm drawing this picture, because all of these functions sort of represent a picture, this is saying h of x is always bigger than everybody. So let's say that h of x looks something like this, where h of x is always on top. We'll call this guy h of x. And g of x is always on the bottom. And so here's g of x. And you know, I have these little equal to signs, so they're, you know, like the greater they're equal to, so I guess at one point they could actually be equal. And what the squeeze theorem or sandwich theorem implies is, like, let's say you got a function that's always bigger than or equal to everything, and you got a function that's always smaller or less than or equal to everything. But at some point they meet, and you really understand the red function and you really understand the blue function, but you don't know the purple function that much. And so the purple function is just going to do its own little thing. It's going to do some weird stuff all the way through. And you may not know exactly what's going on with the purple function, but since the purple function has to be in between the red and the blue, it sort of gets forced here before it starts doing things. And so another way you can think of it is, oh, it gets squished in between these two functions. And there's a picture of the squeeze theorem. Something gets squeezed in between two. So you have this situation where one function's always bigger, one function's always smaller, and then the function in the middle just sort of gets bullied in between those two. And that's exactly what happens with this particular function, with that sine x over x. I need to talk about this function sine x over x. And to be honest, I have no idea what this looks like, right? And I don't care. Where the 10 or 15 minutes comes in as I talk about, I do some little trig things, I have a little triangle and, you know, set up the triangle, and I'll say that something's always bigger than sine x over x, and then I say that something's always smaller than sine x over x. And we talk about what those things are, and then it turns out that when those things that I know what's going on, when those x values hit 0, those are guaranteed to hit 1. And so what happens is, on the right hand side, something that's always bigger, when x equals 1, this goes to 1. And on the left hand side, something that's always smaller hits 1. And the end result is that we get this little thing that says, if I talk about the limit as x approaches 0 of sine x over x, basically using a picture and some other functions that we know, it gets squished into 1. Now, if you want to know exactly why all that is, it's actually an appendix in the back of your book. You could actually type it in YouTube, and there are tons of people who really love explaining it that'll tell you why it's equal to x, sine x over x equals 1, or you can stay after school and I'll tell you. I like talking about it, but at the end of the day, you don't need to know why. You need the squeeze theorem, but I just talked about that. What you really need to know is that sine of stuff over stuff equals 1. Now, I've actually just changed a little bit. This is sort of the specific answer. The general answer, the general rule for this is, let's see, the limit as x goes to 0 of happy face goes to 0 of sine of happy face over happy face is equal to 1. I like using happy face. It gets us away from the x. And the main idea is I need the thing to go to 0, and I need this thing and this thing to be exactly the same. So what does that look like? Well, let's say I ask about what's the limit as x approaches 0 of sine of 5x over x. Now my rule is, right, so I have x is going to 0, and I get 0 over 0. I can say this equals 1 if, and only if, this thing and this thing are exactly the same. Until those are the same, I can't say it equals 1. So what I have to do is I have to do a little bit of algebra to manipulate it so these two things are the same. So if I have a 5x here, I need to have a 5x here, and the way I do that is I'm going to multiply top and bottom by 5. Now when I look at this, I see that this first of all, I'm getting 0 over 0. I see that these are the same. And pretty much the way I look at this is a big fat 1. And so the limit as x goes to 0, it's going to be 5 times my big fat 1, which is equal to 5. All right. Oh, I also need to talk about if limit as x goes to 0 sine x over x. It's the same thing if you flip it. Like if I have the limit as x goes to 0 of x over sine x, that also equals 1. So sine of stuff over stuff or stuff over sine stuff, you get 1 as long as those things are going to 0. All right? So I've got a couple of examples to see how we apply all this. One example is what if I ask for, what's the limit as x goes to 0 of sine squared 3x over x? And my other example I want to talk about is what's the limit as x approaches 0 of sine squared 3x over x squared? Now, before I talk about either of these, I need to talk about what I consider probably one of the most confusing notation items I've ever seen. I hate it. I wish I could get rid of it, but I can't. And that notation is this thing where I talk about sine squared 3x. So I don't know who came up with this idea. I could probably have the resources to look it up. I just haven't. If I write down sine of 3x squared, everybody knows, every high school student knows exactly what I mean. Like when I'm teaching trig and I say sine of 3x quantity squared, no questions at all. We know this means sine of 3x quantity squared. It means I have sine of 3x times sine of 3x. But somebody, probably 300 or 400 years ago, decided, no, that's too much writing. I don't like writing parentheses and squared. So they said, we're going to have a shorthand way of writing this. So we're going to write it this way. We're going to write down sine squared 3x. And this is going to mean this. And the end result is, this notation just kind of confuses at least 60 to 70% of the high school students that I teach. Yeah, it's fewer, it's less stuff that you have to write, but it just confuses people. So whenever you see this, in particular in a few weeks, I actually want you to write this. But at the very least, I want to remember anytime you see this, it means this. All right. Now, why did I make a big deal about all of this? Well, I want to talk about this particular problem. I have sine squared 3x over x, and I only know, right now we know one thing with trig functions. I know that the limit as x approaches 0 of sine x over x, I know how to handle that. I don't know how to handle a sine squared. So, how I manipulate it is I'm going to rewrite this and say it's the limit as x approaches 0. See that sine squared 3x, that's sine 3x times sine 3x. I'm actually going to write it out twice. So I'm going to write down sine 3x, sine 3x. And then I'm going to have it over x, and I don't know, I can have it over 1 or just leave it off to the side. And so now, when I approach this problem, I look at it and I'll say, when I see limit as x goes to 0, let me deal with this part and then I'll deal with this. Now, as far as dealing with this, I have that 0 over 0. I know how to handle it if these are exactly the same. If that's a 3x and this is a 3x, I know I can handle it. So I need a 3 here, so I'm going to put a 3 here and a 3 here. Well, now I can answer the question. Because when I look at this, I have sine 3x over 3x. As long as x goes to 0, I know this is going to be a big fat 1. This is a 3. And how do you handle this? Well, it's how you handle any limit. We're looking for the y value. So I plug 0 in. 3 times 0 is 0. Sine of 0 is 0 over 1. 0 over 1, I know what that is. That's 0. And so I end up with a 0. So as how I compute this is I want to say 3 times 1 times 0, and that gives me 0. Did I go too fast on that?
Yeah, can you explain the sine of 3x over 3x, sine of 3x over 1, 1, 0, 3? Can you explain all that again, please?
Okay. So are we okay with this part? Are we okay that sine of stuff over stuff is equal to 1?
Yes.
Okay. So as long as these are the same, I can say this part equals 1. Right? Now, and what I probably should have done is done a better job of talking about properties of limits. It turns out properties of limits, I could rewrite this. I could write, whenever you're multiplying two things together, one of the properties of limits is you can rewrite this and say this is going to be the limit as x approaches 0 of sine of 3x over x times the limit as x approaches 0 of sine of 3x. So whenever you're multiplying, you can break this two things apart and say it's the limit of this thing times the limit of this thing. Now, let's approach this. If I want to figure this out, I need these two, I need the stuff on top and the stuff on the bottom to be exactly the same. So I need to multiply top and bottom by 3. Now when I look at this, sine of stuff, my stuff matches up, so this is now a big fat 1. I have 3 times 1, so this part ends up being a 3. And now if I want to compute what's the limit as x approaches 0 of sine of 3x, if I plug the 0 in, I get sine of 0, which is 0. And that's where I get my 0. Did that make sense? Or no? Yes, no, maybe.
Why is sine of 3x over 1 0?
That's the limit as x goes to 0. So when you're computing a limit, you're looking for a y value. Like you get to plug this x value in. And 3 times 0 is 0. And what's sine of 0?
0.
0, right? Remember I had in the chart, there are a couple of trig things you have to know, like on a daily basis. Those things that you have to know on a daily basis are that sine of 0 is equal to 0 and cosine of 0 is equal to 1. And so when you're computing a limit, right, you're looking for a y value. You're looking for what happens when you plug the x value in. I don't know did that help?
Yeah, that makes sense. Thank you.
Okay. All right. So there's this example, right?
I have a question on the first part of the equation.
Yes.
So before you started to do any of that and separate the equations,
Mm-hmm.
because it's sine squared sine squared 3x, can't you also just multiply both sides, the denominator and the numerator, by 3x squared, and then you level both of them out, and then just 3 times 0, 0. So you want to get to do what you were saying, if I want this to be exactly the same, I think I'm actually going to hint on that on the second problem. Okay.
And your life's going to, I'm a little worried, because when you see this sine of 3x quantity squared, I want you to realize it's two separate things that are multiplied together. That two separate thing idea is going to make your life a little bit easier when things get complicated. And that's kind of where I'm going with this. All right, so the second one. So now this is sine squared 3x over x squared. What's our answer? Well, first, I only know sine x over x. I don't know the sine squared part. So, but I do know that this means sine of 3x quantity squared, so I'm going to write it down twice. So when I write this down, that's going to give me the limit as x goes to 0. I'm going to write that as sine of 3x times sine of 3x. And that x squared I'm also going to write as an x times x. So if I multiply this together, I end up with what I started, with my original question. But now I get something that looks like that formula that I know. So how I deal with that formula that I know is I need this stuff to be the same. So if this is a 3x, I need a 3x down here. So I'm going to multiply top and bottom by 3. If this is a 3x, I need a 3x down here. So I'm going to multiply the top and the bottom by 3. And then I go through, and I know sine of stuff over that same stuff is a big fat 1. So this is a big fat 1, and this is a big fat 1. And so now I end up with 3 times 1 times 3 times 1, and now I get the 9. Which I think is what you were getting at. But to me it seems simpler if I go ahead and write them down separately. So that was Kevin that was talking about just like squaring it and creating like a 3x squared at the bottom, which is that's essentially the same idea, but there's times where things get complicated and just breaking it apart makes life a little bit easier.
Yeah, but like you said, like if you do it that way, sometimes it gets complicated. I just tried that original way on this formula and it doesn't seem to work.
Oh, well, in that case, do it this way. Because that way I know works, right? So that's okay. All right. So since I only have a 45-minute class period instead of 55-minute class period, instead of getting 2 examples, you're going to get 1 example with 2 ideas. And here's that example. I want the limit as x goes to 0 of tangent of 3x over sine of 5x. That's a little more legible. So what do we do? Well, what always happens in math is I get whatever you're given, you have to, like right now we only know one way to handle trig stuff. The only way we know how to handle trig stuff in these limits is if I can somehow get it to look like sine x over x or x over sine x, then I have something I can do. But I don't have that, right? I've got tangent. Well, actually, the first thing you do is you plug in 0, and 3 times 0 is 0, so tangent 0 is 0, and 5. I end up with tangent 0 over sine of 0, which is 0 over 0, indeterminate form, meaning we have to do more work. And to be honest, the only thing I know how to deal with is if I have sine x over x, and I don't have that here. In fact, I have tangent, and I really don't like dealing with tangent. So, what do you do with trig? Well, all that fun stuff with the identities, you have to use it here. So, I'm going to break this apart. I know tangent sine over cosine, so I can write this as what's the limit as x goes to 0? Well, tangent's going to be sine of 3x over cosine of 3x. And then we still have that sine of 5x on the bottom. Now, as far as dealing with, I need this all in one fraction. I don't need layered fractions. And there's a couple of ways you can rewrite this as a division problem. This is just how I look at fractions. And I have a feeling some of you look at fractions the same way. Obviously not related to this problem. I'm just going to write down some generic fraction, say 7 over 5. And the way I deal with this is I always see 7 over 5. I see this as 7 times 1 over 5. Where you can take the top, move it over, and just make sure you put a 1 on top. So Anytime you see a fraction, you can always take the top and slide it over. Well, I have a fraction. I'm going to take the top and slide it over. So if I do that, that's going to give me, what's the limit as x goes to 0? If I take the top and slide it over, that's going to give me sine of 3x over cosine of 3x times 1 over sine of 5x. Does everybody see that little, just take the fraction, take the numerator and move it over to the front. Now, remember, I still only know this. I only know how to handle if it's sine x over x, and I don't have that here. I've got sine, I still have this random cosine floating around, so what do? Well, anytime you've got a bunch of trig functions floating around, I'm going to break this up. Since I have 3 trig functions, I'm going to break this up into 3 fractions. So when I break it up into 3 fractions, this is going to be the limit as x goes to 0. I'm going to write that as 1 over cosine of 3x times sine of 3x over 1 times 1 over sine of 5x. Okay, I just took that once, like all of my trig functions, I just made everybody get their own fraction. Now, what do we do from here? Well, this looks like it's more complicated, but there's something that makes life a little bit easier. I'm not going to worry about this, right? It turns out I don't need to worry about this. This one's fine, and we'll get to that, why it's fine in a little bit. But this I've got to worry about, because this needs to be sine x over x, and this needs to be an x over sine x. So somehow I need an x. Well, you just can't put an x somewhere. Like if you put an x in the bottom, you got to put the x in the top, which is exactly what we need in this situation. Like if I put an x in the bottom, I can put an x in the bottom here, but I need to put an x up top here. And right now, this is algebraically equivalent to what I started with, but now I can solve the problem because I see sine of 3x over x. I need to make these the exact same number, so if this is a 3x, I need a 3x in the bottom, so I'll multiply the bottom by 3, and whatever I do to the bottom, I got to do to the top. And a similar thing happens over here. I see sine of 5x, so if I have a 5x and I have sine of stuff, I need this stuff to be the same, so I'll have a 5 on top and a 5 on the bottom. And now we're going to compute our limit. And here's how we're going to compute our limit. This says, what's the limit as x goes to 0? Meaning, let's plug in 0 for x. Well, if I plug in 0 for x, 3 times 0 is 0. Cosine of 0 is 1. So this becomes a big fat 1. If I plug a 0 in here, right, that gives me the 0 over 0, which that's where we have our little, this thing where the limit as x goes to 0. Anytime you see sine of stuff over stuff, as long as things are going to 0, you get a 1. So this becomes a big fat 1. And when I look over here, I have sine of 5x, and these are the same. This becomes a big fat 1. So I've identified everything that became a 1, and I've plugged in the x. And so now when I multiply, it's going to be 1 times 3, and then it divided by 5. So I ended up with 3 over 5. Did that?
What was the step?
What?
What was the step where you changed the 1 into an x on the second and third fraction?
So what I did, so those 1s were just placeholders, right? Right. I'm just the 1s are placeholders. They're just sort of guaranteeing I've got some place for the denominator and some place for the numerator. And if I'm going to use this rule, it only works if I have sine of x over x. I need an x in the top and the bottom. So originally I didn't have an x in the bottom here or an x in the top. And you can't just add. Like I couldn't just put a 3 here. What if I put a 3 in the bottom, I got to put a 3 in the top. The same thing is true for x's. You just can't put an x in the bottom. You have to put an x in the top. But what I did is I put an x in the bottom of this fraction and put an x in the top of this fraction, so I could get the pattern. I could make this look like that, so I could say the answer is 1.
Oh, eventually they equal 1.
Well, this part does. Sine of stuff over stuff, as long as these things are the same and x is going to 0, this is going to be 1. What I circled was the big fat one.
So let's multiply.
Yeah, these are being multiplied.
Can you explain the part was 1 over cosine 3x?
All right. Well, here, let's just say I gave you the problem. But what if I just gave you the limit as x goes to 0 of 1 over cosine of 3x? How would you compute that?
Just plug 0. Oh, cosine of that is 1. My bad.
Are we okay? All right. So, I've got my one little rule. I should probably write it a little as far to the right as I can. Oh, I can write it over here. Good. So I can say the limit as x goes to 0 of sine x over x is equal to 1. So that's the only rule I know. Okay. Well, what if I ask, well, what's the limit as x goes to 0 of 1 minus cosine x over x?
That's cut off.
That's cut off. You're right, it is. The limit as x goes to 0 of 1 minus cosine x over x. All right. So guess what happens when you plug 0 in? What do you get?
Indeterminate.
You get 0 over 0. You get an indeterminate form. So that means we have to do more work. Well, we have a problem, right? See, our problem is the only thing we know how to, there's no algebra thing that we can do. Good luck, you can't factor that. You can't multiply, can't get a common denominator. There's no real work you can do to this. And the only thing we know has to deal with sine, right? That's the only rule we've got that helps us do this type of limit. So then we need to revisit some things from trig. And the things from trig we need to revisit, some of those trig identities. Now, before everybody panics about trig identities, 30 years ago, the AP exam was real big about making sure you remembered all of those trig identities from last year. Over the past 10 or 15 years, they don't care so much. Actually, I don't even know if they've had a question that requires that you know it recently, but we're still going to talk about it. And most of you don't know anything about me because I haven't taught you before, but a little bit about me is I have zero memory. I could not remember those trig identities to save my life when I was in high school. In fact, there was only one trig identity I remembered. And that one trig identity I remembered was sine squared x plus cosine squared x is equal to 1. Now, fortunately, that's a pretty good one. It's easy to remember. It's effectively just your Pythagorean theorem. And if I did something like I said, x squared plus y squared equals 1, that's an equation of a circle. X was the sine, or actually x was the cosine, y was the sine. That's how I could remember it. But with this one trig identity, and this and actually a couple others, you could derive everything else. Like for this particular problem, they looked at it and they said, I don't like cosine very much, so I'm just going to divide everything by cosine squared. So if I divide everything by cosine squared x, then, let's see, that's going to give me secant squared x, that gives me a 1, and that gives me tangent squared x. So there's 1, right? You can divide everything by sine squared, that gives you the other one. Those are called your Pythagorean identities because that's like the Pythagorean theorem. As far as the angle addition ones, you don't need to know those at all this year. You used to, but not anymore. Well, so why am I bringing these up? Well, the reason I bring these up is the same reason they're taught in trig, is they let you change things. In particular, this formula lets you change trig functions. If I go through and like if I solve this one and I get sine squared by itself, I find out that sine squared x is equal to 1 minus cosine squared x. Okay. And like the whole time you did, whatever that week or so you did spend on verification, it was to get you used to the idea that those trig identities let you change trig functions. This lets us change a cosine into a sine. If I have a 1 minus cosine squared x, I can change that to a sine squared x. So meanwhile, back over here, I want a 1 minus cosine squared because if I have 1 minus cosine squared, I can change that to a sine squared, and I know how to handle a sine. I don't know how to handle a cosine. Well, how do I get a 1 minus cosine squared? Well, in the interest of time, I'm just going to tell you, we're going to multiply by the conjugate. 1 plus cosine x. Whatever I do the top, I got to do the bottom, which is 1 plus cosine x. And now I have the limit as x goes to 0 of 1 minus cosine squared x over x times 1 plus cosine x. And I did all of that work so I can see that 1 minus cosine squared, so I can change that to a sine squared. And so this is going to give me the limit as x goes to 0 of sine squared x over x times 1 plus cosine x. Now, the way I'm going to deal with this, kind of the same way I did with the last problem. If I see sine squared x, I'm going to write down sine twice. So when I rewrite this, I'll say this is the limit as x goes to 0. I'll write that as sine x over x, because that's what I have here, times 1 over 1 plus times sine x over 1 plus cosine x. So all I did, I took this and I saw a sine squared, so I broke it up sine x and sine x. And then the bottoms multiplied, so I put the x under one of them and the 1 plus cosine x on the other. Now I'm going to compute. When I'm computing limit as x goes to 0, I see stuff over stuff. I see that that's going to be a big fat 1. As far as computing this one, I actually have to plug the value in. When I plug 0 in, well, sine of 0 is 0. And then I plug 0 in the bottom, I get 1 plus 1, which gives me a 2 on the bottom. And if I have 0 over 2, that gives me a 0. And if I have 0 times 1, then I get this whole thing is equal to 0. What's the takeaway from this? Well, if you're ever given what's the limit as x goes to 0 of 1 minus cosine x over x, you could compute it this way. There's nothing wrong with that. And to be honest, that's probably what I did when I was in high school because I couldn't remember it. Or you could remember the second rule that they actually have in your textbook, which is the limit that x goes to 0 as x goes to 0 of 1 minus cosine x over x is equal to 0. So if you look in your textbook, I think at the beginning of the section somewhere they'll have this in a gray box, and then somewhere later they'll have this in a gray box. So if you ever see these two things, right? And honestly, pretty much anytime you see the cosine, you're going to get 0, so a lot of stuff cancels out anyway. But then you get, if you see sine x over x, you get 1. And what I'm really hoping